Okay, welcome to the Chapter 2 Homework 2 review. There was some overlap between the two homework assignments for Chapter 2, but in this one we got a lot more detail into electron configurations and periodic trends, so definitely some new topics from what we covered last week on the homework assignment. The scores on this one were pretty good. We averaged 10 out of 12 as a class, a little bit higher than last week, so it seems like we are starting to pick up some of the Chapter 2 concepts, but nonetheless there are a few things on this that I want to go over. So before I start with that, there were a couple of bad questions on this homework, so I just want to point those out, which I won't be covering. One was there was a fill-in-the-blank question that asked you something about the increase in ionization energy from the periodic table, whether it occurs left or right, and why. It was a really somewhat confusing question to begin with, and then it was set up in Blackboard in such a way that the answer had to be a 14-word answer or so with exactly the right ordering of words. You didn't get the credit. So that was just a terrible question. We do pool questions from different resources, and sometimes some bad ones find their way into the assignment. So I apologize for that, but on that particular one I went through and manually graded all of your answers, and as long as they were correct on the right track, I gave you the point for that. So some of you may see an adjustment in your homework score. Another question which I didn't regrade, but it's not something that will be covered on the test. We had at least one question about the electron configuration of transition metal ions, things like iron 2+, iron 3+, chromium 2+, etc. This is something that was covered in the old textbook we used to use, but is no longer covered in this version of the book, so we're not going to expect you to know that for the exams. It's a little bit different than the electron configuration for main group ions, which we did talk about in some detail. So those ones don't worry about, but the questions that I will go over today during this review are ones that either we didn't do as well as a whole, some of the harder questions on this assignment, as well as a few that classmates requested, and these ones also were ones where I think on the whole we had some difficulty, so it's good to cover those as well. And again, as I always remind you, in the future, if you want me to cover a specific question during these reviews, please let me know and I'd be happy to do that. So we'll start out with some conceptual questions related to energy levels in multi-electron atoms. So really, most of what we covered on this homework assignment towards the latter half of Chapter 2 was dealing with electron configurations of multi-electron atoms and how those electron configurations influence some of the important elemental properties. So the first one is purely conceptual. It's a true-false statement type question where we have to identify the not true statement, the false statement. So let's go through these one by one. So it's which of the following is not a true statement concerning energy levels in atoms? A. In high number shells of multi-electron atoms, some subshells of different shells have nearly identical energies. And this one is definitely true, and this is why, for example, we fill the 4s before the 3d because the 4s is lower in energy than the 3d. So even though 4s has a higher principal quantum number, it ends up being lower in energy than 3d. But these two are also very similar in energy, which is why, as we sometimes saw for chromium and copper, an electron from the 4s can be promoted to the 3d to make a more stable configuration. So this is one example where you have two subshells very similar in energy, even though the one with the higher principal quantum number comes lower, and then we see it again for 5s and 4d, where those two are very close in energy. And then in the sixth row of the periodic table, we see that 6s is filled before 4f, which is then filled before 5d. So you get this overlapping of subshells with different principal quantum numbers. And again, these three subshells, 6s, 4f, 5d, are very close in energy, which is why some of the electron configurations in this part of the periodic table, especially for the 4f elements, are a little bit harder to predict because it's hard to know whether the 4f fills first, the 5d fills first, or you get some combination of electrons in each. So A is definitely true, and it's an important point about subshell energies as we go through the periodic table and go down to higher and higher principal quantum numbers. You're going to have a lot of overlapping subshells that are very close in energy. So in B, in the hydrogen atom, all subshells of a given shell have the same energy. And this is a key distinction between single electron atoms, hydrogen, and multi-electron atoms, which is everything else. So for the hydrogen atom, the subshell energy only depends on the principal quantum number. So that means that all subshells of a given shell do have the same energy for hydrogen. As we saw from the Bohr equation, the energy levels for hydrogen atoms are given by the Bohr constant minus 2.18 times 10 to the minus 18 joules divided by n squared, where n is the first quantum number, the shell number. N equals 1, n equals 2, n equals 3, and so on. And all of the subshells within a given value of n are at the same energy for hydrogen. So for hydrogen, 2s and 2p are at the same energy, but as we saw for multi-electron atoms, 2s is lower than 2p when you have more than one electron. So B is definitely a true statement. And then C is sort of saying the same thing about multi-electron atoms. In a multi-electron atom, the various subshells of a given shell have different energies. This one is also true, because as we saw for multi-electron atoms, the energy level depends on both the first and second quantum number, n and l, the principal quantum number, and angular momentum. So there is no simple equation for the energy of multi-electron atom subshells, but as we saw, 2s is lower in energy than 2p, 3s is lower in energy than 3p, which is lower in energy than 3d. So for a given shell, the subshells always come in the order s, p, d, and f. So for multi-electron atoms, the subshells are all at a different energy for a given shell. Choice D. Orbital energies are usually different in multi-electron atoms than the corresponding one in hydrogen atoms. And this one, as we talked about in class, the orbital energies for hydrogen only depend on the value of n, the first principal quantum number. For multi-electron atoms, they depend on n and l. You have more protons in the nucleus. You have electron-electron repulsion. So while it's certainly true that you could have the same orbital energy in hydrogen and in a different atom, it's not likely. So D is also true. In general, as you add more protons to the nucleus and as you add more electrons to the given subshell, the subshell energies are going to be significantly different than what you would see for hydrogen. And then finally for E, this one hopefully is the false statement, the orbitals within a subshell of a multi-electron atom have different energies. So this is going to be our false statement. So now we're talking about a subshell. Some subshells only have one orbital. So if you have an S subshell, 2s, 3s, and so on, you only have one orbital, so there is no degeneracy to worry about. But we saw that for the other subshells, P, D, and F, you have more than one orbital in that subshell. And so for a given subshell, for example, 2p, we saw that you have 2px, 2py, 2pz, which correspond to the three different m sub l values that are allowed. And whenever you have multiple orbitals in the same subshell, like we have here, 2px, y, and z, those three orbitals are all going to have the same energy. The energy does not depend on the orientation of the orbital, which is the only difference between these three. So E is going to be our false statement, and that's going to be the correct answer here. Okay, so some conceptual questions are often more difficult to tackle because there's a lot of information there, but we definitely want to be clear on what are the factors that influence subshell energy, and that's going to then dictate the order that these subshells fill in, which is a topic we'll get into later. So we do have one more question about subshell energies here, and this is another conceptual one. Which side of these comparisons is incorrect? And remember, in general, when we say more stable, we mean it has a more negative energy. So we know from the Bohr equation, an equation for subshell energy for multi-electron atoms, it's a little bit more complicated, but let's look at the choices here. So for A, we're asking the 1s orbital in hydrogen is more stable than the 1s orbital in helium plus. So these are both multi-electron atoms. 1s in hydrogen, hydrogen has one electron, helium plus also has one electron. The difference between hydrogen and helium plus is the number of protons in the nucleus. So from the Bohr equation, remember we have the energy is given by minus 2.18 times 10 to the minus 18 joules. And then there's also this z squared term, which I didn't mention before, which is not important for hydrogen because z equals 1, and then you divide that by n squared. So this is going to be the number of protons in the nucleus. The number of protons in the nucleus will influence the subshell energy. So we could calculate these for hydrogen and helium exactly if we want to, but the point is that we have this z squared term here, so as we add more protons to the nucleus, the subshell energy is going to get more and more negative. These are all negative numbers. So the 1s orbital in hydrogen should be less stable than helium, because in helium it's going to be a more negative number. So this one's going to be one of our incorrect statements, but there could be others. So if we look at choice B, the 2s orbital in helium is less stable than the 2s orbital in helium plus. So this one we don't have a simple equation to compare, but the difference between helium and helium plus is that we have, in this case, the same number of protons, but we have different numbers of electrons. So helium has 2 electrons, helium plus only has 1 electron left. And so when you have multiple electrons in the same subshell, in this case 2s, same orbital, you're going to have electron-electron repulsions that are going to cause the subshell to be less stable. So the 2s orbital in helium should be less stable than the helium plus because we add this second electron you have electron-electron repulsions, and that's going to drive up the energy of the subshell. So this one is going to be a true statement, so we don't want to include that in our answer. And then finally, choice C, the 2s subshell in lithium is more stable than the 2p subshell in lithium. Alright, and this one deals with subshell energies for multi-electron atoms, and as I talked about in the last problem, when you have a multi-electron atom, lithium has 3, you have the ordering of the subshells is going to depend on the value of L as well. So you have S comes before P, which comes before D, which comes before F. So in lithium, we fill the 2s subshell before we fill the 2p. So for any multi-electron atom, doesn't matter whether it's lithium or anything else, the S subshell comes before P, which comes before D and F if applicable in that given shell. So in this case, the 2s will be more stable than the 2p. So this one is also going to be true, so we don't want to include that in our answer. So the correct answer for this one is A only. A is the only incorrect statement of these three. Okay, so then now we can move on to one last conceptual question. So we've talked about a lot of the factors that govern subshell energies, and now we just want to know in this problem which of the following subshells in a typical polyelectron atom fills last. Alright, so there are no simple equations to govern this, of course. We have to, we don't have any way of predicting it, but the best way to predict it is from the periodic table. So I showed you in class how we can use the periodic table to allow us to tell what order the subshells come in. So we're looking for the one that fills last. This is going to be the one that's highest in energy, or the comes latest on the periodic table. All right, so clearly it's not going to be 1s, because 1s is the first subshell that's filled. But now we have 3 subshells here that are close to each other, 4d, 5s, 5p. Let's figure out what order those come in. All right, so if we go to the periodic table, we have, we're looking at again, 4s, 4d, and 5p. Okay, so 4s comes here, 1, 2, 3, 4. This is the 4s block. And that's going to come before the 4d. Okay, so we have 4s is here, and then 4d is here. So 4d definitely comes after 4s, and then we have also 5p, which then comes after 4d. Alright, so again, the one that we're comparing, 4s is this part of the periodic table, where we're at atomic number 19 and 20. 4d is here, it's the second row of the transition metals, and so that's going to come afterwards, and then 5p is going to be this part of the periodic table, which comes after that. So 5p comes latest in the periodic table, so that's going to be the one that fills last, which is choice D. So the periodic table allows us to predict the ordering for all of the subshells, and again, it's going to be 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. So the ones that are relevant are all listed here. So from the periodic table, we can get the ordering of all the subshells if we wanted to. And again, that's 1s, 2s, 2p, 3s, 3p, 4s, 3d, then 4p, then 5s, 4d, 5p. So of those ones, 5p again comes last. That's going to be the one that's filled last, is the highest in energy. So that's what the Aufbau principle tells us. We order the subshells from lowest to highest energy, and then we fill them in order from lowest to highest energy. So the one that we fill last is going to be the highest energy. In this case of these choices is 5d. Alright, sorry about that. I had to pause there for a second. Okay, so now we're going to start moving on to actually talking about electron configurations. So this question was submitted by a student, and it was asking which of the following atoms has 4 unpaired electrons. So if we're asking about unpaired electrons, the first thing you need to know is the electron configuration, but that alone is not enough, because remember that we have to then follow Hund's rule to fill up the last subshell and see how many electrons remain unpaired. So when you're considering unpaired electrons, you need to only consider subshells that are partially filled. If you have a completely filled subshell, like a 2s2 or a 2p6 subshell, all the electrons in those will definitely be paired. You don't have to worry about them. But if you have any partially filled subshells, then you need to go a little bit further to understand how many of those electrons are unpaired. So let's just do all of these quickly. So choice A is fluorine. So the first thing we need is the electron configuration for fluorine. So it's going to be right here in the periodic table, atomic number 9. So it's going to be 1s2, 2s2, 2p1, 2, 3, 4, 5. All right, so again, it's going to be 1s2, 2s2, 2p5. We only need to look at the partially filled subshell, which is the 2p in this case. So 2p can hold up to 6 electrons. This one only has 5. And so what we need to do then is figure out how many of these 5p electrons are unpaired. So remember that unpaired means it's going to have a certain spin value, spin up or spin down, without another electron of the opposite spin paired with it. So if we look at the 2p subshell, we have 3 2p orbitals in any given 2p subshell. Now we have 5 electrons to put in. So Hund's rule tells us that we fill them one at a time first, all with the same spin. And then that's 3 electrons, and we go back and add the last 2. So these two are going to be paired. They have one spin up and one spin down, so we only have one unpaired electron here. Alright, so fluorine only has one unpaired electron. We're looking for the one that has 4, so it's not going to be this one. For B, beryllium, we don't even have to do this much work because beryllium is going to be right here on the periodic table. The configuration for beryllium is 1s2, 2s2. In this case, both subshells, 1s and 2s, are filled, so there's going to be 0 unpaired electrons. And that's because we have all filled subshells. Alright, and then choice C is carbon. And many of you picked choice C as your answer, and we'll go through in a second and show you why this isn't the case. So for carbon, you probably got the electron configuration right, which is why you picked it. So carbon is atomic number 6, 1s2, 2s2, 2p2. Okay, so carbon has this configuration, and I think many of you thought that unpaired electrons were valence electrons. So carbon does have 4 valence electrons, 2 2s electrons, 2 2p electrons, but we're only looking for those that are unpaired. So again, we look at the partially filled subshell, which is 2p, and so for the 2p subshell, we have 3 orbitals, and when we fill the orbitals using Hund's rule, we have 2 unpaired electrons. There's only 2 electrons in the 2p, so there can't be more than 2 unpaired. Okay, so this one's also not it. And then finally for D, oxygen, I think many of you picked this one as well. And again, you got the configuration right for oxygen. So oxygen is 2 elements past carbon, so it's going to be 1s2, 2s2, 2p4. So again, I think a lot of you picked oxygen because you saw, oh, there's 4 electrons in the 2p, then there's 4 unpaired electrons. But these are not all going to be unpaired. So again, when we fill this using Hund's rule, for oxygen, we have 4 electrons, so we go 1, 2, 3, 4. These 2 are paired. We only have, again, 2 unpaired electrons. Alright, so that leaves iron by default. We can verify that this has 4 unpaired electrons. So for iron, I'll do it up here. Iron is a transition metal. It's here on the periodic table, a little bit lower than what we've been seeing. So the noble gas before it is argon. There's not going to be any unpaired electrons in the core, so we can write the sort of the abbreviated configuration here where we have argon is the previous noble gas, and then after argon we're in the 4s part of the periodic table. This is the 4th row in the s block, so 4s2, and then we have 3d, 1, 2, 3, 4, 5, 6 to get to iron. Alright, so it's going to be 4s2, 3d, 6. So here the partially filled subshell is 3d, and in the 3d subshell there's L equals 2, so 2L plus 1 is going to be 5. There are 5 d orbitals. Oops, that's only 4. Making a little bit smaller. So there's 5 3d orbitals that we have to fill. And follow Hund's rule in doing that. So it's going to be 1, 2, 3, 4, 5, 6. So these 2 are paired, and then these 4 here are all unpaired. So iron does in fact have 4 unpaired electrons. That's going to be the correct answer, which we sort of got by elimination by doing the other 4. Alright, so anytime we ask about unpaired electrons, you do need to make sure to not only determine the configuration, but also fill the orbitals using Hund's rule. Alright, another related question about electron configurations. We gave you here, in this case, the partial diagram for the 2s and 2p, and you had to identify the element, and then as well as its group number, partial valence orbital diagram. So we asked you for the configuration, the electron, the identity of the atom, and the group number. So here we have 2s2, 2p3 as our valence electrons. So if you go to the periodic table, the 2s2 is here, and then 2p3, 2p1, 2, 3, that identifies this as nitrogen. Now most of you identified the element correctly. So this is going to be nitrogen, and then the full configuration is going to be helium, so those are the core electrons, and then 2s2, 2p3. So many of you picked choice C because it has the correct configuration, it has the correct element, but then we didn't look here at the group number part. So when we give you these group numbers, the periodic table that we give you guys has Roman numerals. So there are three numbering conventions for the periodic table. So the one uses these letters, A's, and B's, and that's kind of the old school numbering system, which is what your periodic table has. But we give it to you in Roman numerals. So it's 1A, 2A, then you have all the B groups, and then 3A, 4A, 5A. So Roman numeral 5 here. So nitrogen, using the older system, is actually in group 5A. And here we have 7A. So that's not correct, 7A, 17. Now the number in parentheses here that we also give you is sort of the alternative numbering system. We're never going to mismatch these for you, but there's the other way of numbering the groups in the periodic table is just straight across 1 through 18. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So nitrogen would be in group 15 using the other alternative numbering system. That numbering system is easier, but it doesn't tell you as much about the valence electrons, which is why it's often not used. But nitrogen is in group 5A, which alternatively can be called group 15, but this answer choice had 7A, 17, which is not correct. So choice C was what most of you picked. That's not the correct answer, and in reality the correct answer is none of these. None of these have the correct symbol, configuration, and group number. Okay? And then one other one I'll go through, I have I guess 2 left now, is dealing with atomic and ionic radii. So we want to know which of the following has the smallest radius. So here we're including neutral atoms and ions. If we have neutral atoms, we can use just the periodic trends that we taught you. So for neutral atoms, the radius increases as you go down, and it decreases as you go left to right. And we have that basic atomic trend, that basic periodic trend to tell us about atoms. But when you start talking about ions, you have to also think about the electron configuration and think about some other things. So the periodic table is not going to directly give you a trend for ionic configurations, because it really depends on how many electrons that ion has. So the first thing we should think about for these is the valence configuration. So phosphorus is going to be 3s2, 3p3. Cl minus is also going to be in the third row of the periodic table. It's going to be 3s2, 3p6 for the valence electrons. I'm not showing the core electrons here because valence is really all that matters. Aluminum is also in the 3p. It's going to be 3p1 in this case. And then S2 minus, same story. Right here in the periodic table, you add 2 electrons, it becomes 3p6. And then finally, gallium is down below, and it's going to be 4s2 with those 3d electrons as well. But the point is that the last subshell that's filled in gallium is 4p. So if we're looking for smallest radius, the first thing we should do is pick the one that has its valence electrons in the lowest shell number. So this one is going to be the 4th shell. All the rest are 3rd shell, so we can eliminate this one. But now we have to compare these ones. And most of you picked Cl minus because chlorine is furthest to the right, so you thought it was smallest. But if we look at the configurations here, we're adding extra electrons to chloride and sulfide. And one thing I didn't really talk about in a lot of detail in class is that, but as you add electrons, you're going to increase the radius. So in general, if you have an atom and an anion, so we have 2 atoms, 2 anions, all in the same row of the periodic table, if you have even one extra electron in there, the anions are always going to be bigger, regardless of their location in the periodic table. So Cl minus, even though it's further to the right, is going to be way bigger than phosphorus and aluminum. So we can eliminate the anions. Whenever you're comparing species from the same row of the periodic table, if some of them are anions, the anions are always going to be way larger. So now we're just looking at the two neutral atoms and picking the smallest. So aluminum is here, phosphorus is to the right of aluminum. Because they're both neutral atoms, we can use the periodic trend. Phosphorus is to the right, phosphorus is going to be smaller, so that's going to be our correct answer. So really the important point here is that when you have extra electrons, the radius gets way bigger. I mean, if you look at atomic versus ionic configurations, the radius can sometimes almost double just by adding a single electron. So it's a very big effect when you add extra electrons. And so we're comparing atoms that are neutral to ions that are negatively charged. The negatively charged ones are always going to be larger as long as they're in the same row of the periodic table. And then finally, the last one here is which of the following best describes the set of elements below. We have arsenic, lead, and helium. So we have to find them in the periodic table and then understand where their location is in the periodic table and how that affects their, some of their properties. So the easiest one here is going to be helium. So helium is a noble gas. It's on the right side of the periodic table. So this one is definitely going to be a nonmetal. Alright, so that one's probably the simplest one to identify. All of the noble gases, everything all the way over on the right of the periodic table is a nonmetal. So anything that doesn't have helium as a nonmetal, we can quickly eliminate. So there's a little bit of game theory involved with doing some of these multiple choice questions. So pick the easiest one first. In my opinion, helium is the easiest. So it's definitely, helium is not a metalloid, helium is not a halogen. And so now we're left with choices A, B, and D. So if we look at arsenic here, the choice A says that arsenic would be a transition metal. Choice B and D has it as a metalloid. So which of those is correct? So remember, transition metals are only those that are in the D block of the periodic table. That would be group 3B through group 2B as is numbered in our periodic table. The numbering system for transition metals is weird, but it's just this block of the periodic table, starting at scandium to zinc for the first row, yttrium to cadmium for the second one, lanthanum to mercury in this one. So these 30 elements here, plus some man-made elements below that we don't really care about, those are going to be your transition metals. So arsenic is over here, it's in the P block, so the P block is not the transition metal block, so we can get rid of choice A. And arsenic is in fact a metalloid, so arsenic is one of those elements that's right on the staircase borderline, and is one of our 6 commonly identified metalloids. So then finally we have to look at lead. So choice B has lead as a main group metal, choice D has it as a transition metal. And as I just said, the transition metals are all going to be in this portion of the periodic table in the D block. Lead is over here. It's a P block element, but that doesn't necessarily mean it's a nonmetal. So remember, the staircase goes down like this, and lead is to the left of that staircase that divides metals from nonmetals. So lead is a metal, even though it's in the P block of the periodic table. And so it's going to be choice B is the correct one, where lead is a main group metal. Choice D has lead as a transition metal, which is clearly not the case because it's not in the D block. Alright, so we have to remember that there are two different main classifications of metals. There's main group metals and transition metals, as well as the intertransition metals, which are the F block down here. But main group metals include all of the S blocks of the periodic table. These first 2 columns are main group metals, but there also are some main group metals over here in the P block. So aluminum, gallium, indium, tin, thallium, lead, bismuth. All of these ones sort of on the lower left side of the P block are also metals. As long as they're not right on that staircase or to the right of it, they are still classified as metals. So some of these ones down here, as I'm pointing to, are going to be also considered metals as well. Alright, that takes us to the end of our review. Please ask me any questions you have about this. If there's anything I didn't cover, feel free to contact me. We'll be back at it again next week with Chapter 3.